Next we have high temperature pyrolysis. Andrew White, another company that's been interesting to watch, fun to watch over the last few years, developing high quality biochar using high temperature pyrolysis. Andrew?
Appreciate it. Okay, good afternoon, everyone. Thanks for sticking around for the last session of day 2. Very much appreciate it. So we'll be talking about developing high quality biochar using high temperature pyrolysis. Additionally, part of the talk will be on the importance of developing co-products to aid in the financeability of said plants and projects. So the real quick, who are we? So, we operate in a couple of different groups. We've been around now for 10 years developing the pyrolysis technology. We've got a couple other small engineering groups and consulting services. But from the pyrolysis side of things, we have an engineering group and project management group called CHAR Tech Solutions. We do R&D and broker biocarbon through CHAR Tech Biocarbon. And we have a services group. This group operates plants, but also we ended up building our own lab to test feedstock and biochars, both proximate, ultimate energy through bomb calorimetry, grinders, because we found one of the key advantages of high temperature pyrolysis is control, the ability to tune. And if we're going to tune, we need to know what we're putting in and what we're aiming to get out. So we've got a pretty great lab at our Thorold facility. So maybe some simple pictures on sort of defining things, how we see them. Tried to find the simplest ones possible. Obviously, combustion, direct air, put a big pile of stuff together and burn it. Gasification, what I used here is just a picture of traditional charcoal making. And the point is that in those cases, I don't have to get too much into it thanks to our previous presenter, but you're introducing a small amount of oxygen, a limited amount of oxygen to burn some of the material in there to create your heat. All sorts of great engineering designs, but just to keep it simple, that's how sort of a gasifier works. And there's a pretty broad temperature range depending on the gasifier design, controls, etc. We'll call what I call standard slow pyrolysis, generally between 450 and 650 degrees Celsius. That's now an indirect system. So sort of the general layout is you have your kiln, you create your syngas that goes directly to an oxidizer that creates a flue gas that's hot. It goes into the shell of the kiln to try and transfer heat from that gas through the tube, the heat tube that the material's in, and into the material. So you kind of have an upper limit on temperature on those systems. And then finally, where we operate high temperature pyrolysis, that again is an oxygen-free system. The difference is we have burners in our sort of pyrolysis kiln directly under the heat tube. So we're operating at higher temperatures. And fundamentally, why we want to do that is a couple things. One is, like I said in my last slide, control. So we can have multiple heating zones. If there's a plug of moisture in our biomass, the temperature of the kiln will drop and the burner will ramp up to accommodate it. Running at those high temperatures also increases the yield of a nice high quality gas, which I'll talk about. So we don't really aim to produce any bio oils, and we don't need to burn the gas before it cools because we're operating at those higher temperatures. And it also allows us to get that higher quality biocarbon. So I'll talk a little bit more about what that market space looks like for us, but meeting pretty stringent carbon specs is a crucial element of what we do. Looks like I just said all those things, so that's great. Like I said, if you look at more standard pyrolysis, one of the key control requirements is getting that pyrolysis gas directly into that oxidizer as quickly as possible, so you don't have a condensation of tars and oils and other condensables. If you operate at a higher temperature, you're able to crack a lot of those within the reactor, and so therefore your sort of gas treatment train can be a little bit different because you're not going to have like a 30% oil tar mix to try and condense and deal with. Those numbers come way down, and all of that gets converted into more gas, which is fantastic. And for us, that then allows excess gas to be used and marketed and sold. So we'll talk a little bit about the gas in a second, but our aim today is converting it into renewable natural gas because there's a fantastic market opportunity for it. You get 20-year offtakes that can really underpin a project. In future, green hydrogen is actually easier for us. There's just not, there's a lot of talk and hype, and then you get into compressors and 200 kilos in a truckload, and where are you going to move that? And there's certainly some challenges, but we can make it. We just need to find the opportunities to move it. With high temperature pyrolysis, really what we're after is how do we extract the maximum value from that biomass that we take in. So active projects, so we have 2 projects in construction right now. I'm going to focus on the Thorold project. So that's our facility in Thorold, Ontario, which is straight across the lake from the city of Toronto. That will have an output of 10,000 tons a year of biocarbon, which is going to go to steel making, and about 500,000 gigajoules of renewable natural gas. We're going to have some initial operations starting this summer, so we're well into the development and construction of that project. The second one, this panel is not on biosolids. There was a previous one on biosolids and sewage sludge, so we are building a project for Synagro, which is the US's largest biosolids processor. That one will also be coming online in 2024. A little bit different requirements. Number one is the destruction of PFAS, but through high temperature pyrolysis, we can really see that PFAS destruction by maintaining a high temperature, and we can create really high quality syngas that can go back to the dryers on that system. So a little bit more about Thorold. So that's where our facility is. You can see Toronto straight across the lake. I live in Toronto, so I can see the plant, and then I have to drive all the way around in the morning, which is a real pain. But for us logistically, ArcelorMittal Dofasco, who's our off-taker, is just down the road. In the green circle there is our building. We're actually on a former Resolute pulp and paper plant, and we're in the former wood room. So when we moved in, there were still some giant debarkers that got taken out, and now we're putting our system in there. But we're on the Welland Canal, which is part of the St. Lawrence Seaway. So we have seaway access, rail, and truck behind us. So quick rendering of what we're building and kind of why we're building it. We have 2 processing lines here. One's green, one's yellow. The yellow one looks like there's a little bit more equipment. That's because we have a dryer in that line. With our location close to Toronto, we can get a lot of clean pallet wood. So that's already very low moisture, 15-20%. So that can go straight into the system. For flexibility, we can bring in forestry residuals as well, but we obviously need a dryer to do that. Storage is really there just for 3 days, and storage is a really interesting element to think about when looking at larger scale industrial processes for biocarbon production. One is from financeability. Generally, people who are financing projects want to know that you're never going to run out, so they want a lot of storage. On the flip side, most permitting agencies want as little storage as you can get away with. So in this particular case, our feedstock supplier is half a mile down the road, and they already have a license to aggregate. So we're just getting enough storage here to last for a long weekend. So we can basically have 3 days of storage when they're not running trucks. They're doing the initial grinding, so we're taking it in at a hog fuel standard, so 3" minus, directly into, out of walking floors directly into the system. Our kilns are kind of in the background there in the building. We then go through a agglomeration process to densify into a silo and then into a truck. Plan of this scale is probably doing 1 truck a day of biocarbon out because we are agglomerating it. So our densities of our biocarbons in the range of 500 kilograms per cubic meter, which I think is low 30 pound per cubic foot, plus or minus. So, we really want to get that density both for logistics, but also for our clients. So in this case, our client is ArcelorMittal. One of the world's leading steel manufacturers. I think they are the biggest outside of China. And I took this picture from their 2021 Climate Action Report. And so when you look at decarbonizing heavy industries like steel, you'll see a lot of this sort of, I'll call them the standard approaches. We're going to use hydrogen from renewable energy, which is good and important. We're going to use carbon capture, which is a key element. You do kind of need all these things. In the bottom center, it's probably hard to see the writing, but it says DRI-EAF. That's direct reduced iron and electric arc furnace. That uses way less coal than a blast furnace does, but you still need some fixed carbon in that electric arc furnace for the chemistry of steelmaking to happen. So when we look at a standard steel plant, they're still going to need between 30 and 50,000 tons a year of solid carbon in the reactor, in the electric arc furnace to make that steel. And before sort of full disclosure, they've invested in CHAR. So why are they investing? Because they identified pyrolysis as a key step on their decarbonization pathway because of the need for that low GHG biogenic carbon product. So a little bit on, that's sort of the background in a sense on why we're focused on this market, because our production levels versus the demand, there's a big gap there. Sort of, I'd say, unlike a lot of the biochar, if we're producing product that meets the spec, we can get it moved very quickly. But it's a pretty tight spec. Fixed carbon, I said higher than 85. In general, we're looking at, it's got to be no more than a couple percentage shy of 90% fixed carbon. Low ash, we have to be careful of specific ash components, so that speaks more to feedstock. Low volatile matter, I put less than 10 here, often it's less than 5. To get that kind of a volatile matter in your biocarbon, you do need to run at those higher temperatures with reasonable residence times. Relatively high energy density. So all of these are controllable in a higher temperature process, which is why we chose to go down that path. And then once you produce your biochar, it's sort of the granulometry or the shape or the feel. Is it a powder? Is it a pellet? What size are the pellets? What type of pellets? What kind of binders are you using? What are the density limitations? How do we integrate it in the system such that the steel producer doesn't need to buy a bunch of new equipment? So all of these are really, really important factors. And each type of use case needs a different form factor and a different spec. So if we're going in a blast furnace, pulverized coal injection is obviously a bit of a powder. If you go in with the burden as like a nut coke, you need a much more dense, hard material. Electric arc furnaces are different. Other metals, copper, nickel, alumina, they all require solid carbon. So I think it's a really good opportunity for people looking at the general space of biocarbon to think about what other market opportunities are there to move some volumes of product. Like I said before, we do produce two products. One's the solid carbon, the other's a gas. And what I really want to highlight here, besides saying, hey, we got lots of hydrogen, which is great, is again the level of control. So there's a real quick chemistry. There's a reaction called the water gas shift reaction. You take carbon monoxide and water, you make hydrogen and carbon dioxide. Those sort of arrows going each direction in the middle mean that's a reversible reaction. So we can find an equilibrium point and we can drive that reaction either direction. And if you look really closely at the graph, what you're going to see is the CO line goes down while the CO2 and the hydrogen lines go up. So when I talk about control, this is the type of control that we're after. We can find that equilibrium point and we can hit it with the reactor and we can watch these gases do their reaction. So obviously we want more hydrogen. We push the reaction one way. We want a little less hydrogen for a couple reasons. There's a couple applications where we may look at that. We push it the other way, but this is where the control is critical to make these higher quality outputs. So that's the water gas shift. The second reaction we like to focus on, and this happens after the pyrolysis reactor, is called methanation. So this is where we make methane, which is the main component of natural gas. That's how we're creating renewable natural gas. Why we love renewable natural gas, particularly in Canada, is the gas utilities will sign 20-year offtake agreements at prices that are completely independent of what, say, the Henry Hub natural gas price is. It's not related to it at all. It's about a 5x premium to fossil gas, and they'll lock in for 20 years indexed to inflation. So when we talk about project financing and how do you get lenders involved in a project, this is a really great way to make that happen. Typical renewable natural gas comes from anaerobic digesters, organic waste, landfills, and the like. The government of Quebec commissioned a study that was done by Deloitte and WSP to look at what's the opportunity to make renewable natural gas in places like Quebec. And what you see in 2030 is that there's a little sliver at the bottom. The units are 25 petajoules. That's 25 million gigajoules, which is roughly 25 million MMBTU. That's from sort of typical organic waste. When we look at existing forestry residuals, so the purpose of the study was to look at what's existing in the province. Between non-merchantable wood, harvesting residuals, and processing residuals, the opportunity for RNG goes from 25 to 140 million MMBTUs, rough conversion. So there's a really great opportunity to continue to find ways to add more and more value to these residual streams through different technology offerings. Non-dilutive government funding, I think, is also still key. So we're pretty keen on doing that for de-risking. For our Thorold plant, we were able to get $14 million from the governments of Canada and the province of Ontario. And I think anything at this scale, that's really a crucial step. I think probably most people in this room know the challenges of financing. So, whether it's a Canadian or a US application, do we have PCTs, ICTs, grants, government-backed loans? All of these programs need to be advocated for. We're doing a lot of advocacy in Canada and in both Ontario and Quebec to push these and help people understand that this helps climate, this helps job creation, this helps forestry. It helps a lot of industries. And so getting that voice together is crucial. So, maybe a bit of a call to action, make sure you're talking to your government officials and getting them to really understand all of the benefits of processes like the production of biochars and biocarbons. And then a quick plug for us. This is what we're planning to do over the next few years. So we're in the process of building our Thorold project. We have 3 more that are in development. So we've identified sites. We've got feedstock locked up through some LOIs. We've got offtake agreements. And then we've got 4 more where we've identified sites and partners, and we're moving it forward. But as a general comment for the room, we have a bit of a proprietary element around our pyrolysis technology, but we are very much on the development side. So we are looking for partners from equipment vendors on the front end, back end, feedstock suppliers, financial. We're funding these at the project level. So we're keen to collaborate with those in the industry. And then one final, maybe as we look at scale, the question always becomes, where are we getting the biomass from? How far are we moving it? And I think importantly is what's the quality of that biomass, and how do we sort of advocate for a bit more of a standardization so people understand what is wood waste, what is clean wood waste, what is forestry residual. Our approach, we kind of borrowed it from EcoStrat, if anyone in the room knows EcoStrat, in terms of setting different grade levels, and that's what we are advocating for with our government in Ontario around our permit applications. So you kind of look at this pile and you say, well, can you make biocarbon out of this? And the question always is, it depends. There's a little bit of glue in there. There's a painted skid in the back. There's some laminate. I don't know. It really depends on what you're trying to make and what your permit allows you to do. And so I think this will be out there on the deck, but this is sort of what we agree with, certainly with what EcoStrat's doing in terms of the different grades from A to D. And speaking a common language, I think, is really important as we look to bring people outside of the industry in and help them understand the process. So, helps you understand the chemistry, helps you talk to suppliers, helps you talk to permitters, how much is allowable. If I'm getting wood waste, can it be 5% contaminated with certain things? And I think that's a crucial point for project financing as well. So I tried to cover a few different things that we think is important. Contact details are there. Andrew Friedenthal is sitting over there. He's with CHAR Tech as well, so feel free to come chat with either of us or reach out to us after the conference. So thanks very much.
Biochar.org appreciates the support of our sponsors, exhibitors, presenters, and attendees. We look forward to seeing you at our next conference in September 2025.